last class, we studied mathematics and its operation by from more generalizedly, and also learned how to apply to linear system. And actually, I have ever mentioned the linear system. Many problems in real world can be written linear system. After one student come here from the next class, then I will explain one more, and by giving an example, what problem can be represented to. Maybe I'm going to speak English, but maybe he's not foreign. I just noticed the homepage in our school, our university. So maybe I have never any information for him or her. So if he has any class in this time, then I might change this time to another day. Of course, he can participate in this time, then I will let continuously. The final concept of the last class was n powers of a, so it is written like this, and it is the product of a and n times of a, and a is matrix. So from this, we defined matrix polynomial. It is similar to polynomial, and if we have matrix A and polynomial B, then we might be able to write P of A, and it is called matrix polynomial. And we defined A to the n, so it might be well defined. It might be well defined. Might be and would be. It is clear now because we have any polynomial. If I have this, then by substituting to a x as a as ax, a will be written a squared to a plus 3, and it gives only one matrix. Square. It gives us only one matrix with same size with A, So it is well defined already. It is well defined. And also I mentioned some things that proposition. I will write simply. It is similar to the real polynomial. In this case also x squared x cubed is x to the 5, and it is same x3 products x2 x to the 2. So it is satisfied in matrix polynomial. And then next I will explain transpose, and it is also a kind of important information in matrix. As a brief note, it is similar to inverse matrix. To explain this, I will define first that A be a square, not A be on rectangular matrix. Then the transpose matrix of A denoted A to the T by A to the T, and is the matrix transpose the matrix. That means i's row and j's column entries same of A matrix is same to j's rows and i's column of A transposes matrix. Let me give a simple example. So if 1 1 1 2 2 1 2 2, it is let A be a matrix like this, then A transpose is A11 A21 A12 A22. So it is changed the entries. And before I explain this, I explained a little. It is similar to inverse, and I will explain a little because if I explain it in detail, you need to study dual system. So okay, I will explain dual system a little. It might be okay you didn't understand yet. We might consider a map from vector space to vector space, and if we have a map from W to it is vector field, so it is vector space, so we might have field, and we construct a map from W to F. Then its dual is defined. W composition T, and then W's domain is W, and its codomain is F, and W composition T's domain is V, because if it get an element of V, then it will give element of W by T, and it will give an element of F. So if we give some W's information, and it will give V's information. So the dual system is a kind of inverse map that preserve the structure. In this concept, the structure was vector space. So because original map was from V to W, but the dual map goes to W to V. So if we represent this to matrix, then it will give this transpose of T. So in this sense, I said transpose is similar to inverse to preserve the structure. I wanted to just mention it is similar to inverse. So if you couldn't understand of dual contents, the contents of dual, it is okay. I might explain the further chapter. Okay, then let's get back to original. I will give some property of transpose. For matrices A and B, its size is can be performed the next statement. Then a transpose is A because we defined just changing the entries ith row and j's column to j's row and ith column. So if we perform it one again, a transposes J, I is a transpose IJ. So it is same to original matrix. And next, similarly, if you give the entries, if you define this matrix's entries, then you will get the distribution rules from the transpose, and also it is same to satisfied to other subtraction. And for the scalar multiplication, it gives just it is also similar to distribution rule, but the scalar is, we might consider scalar is just 1 by 1 matrix. Then its transpose is itself, because there is no on-diagonal matrix. Can be considered as a matrix. Of course, if we product n times n matrix with 1 by 1 matrix, then we cannot product it. We will just product for each side. So it sometimes it is if we forgot the structure of matrix, then it is same, because if we consider the real number 2, the 1 by 1 matrix over real number, then if we get some number, then we will give a matrix, and it will be bijective. So in the set perspective, it is same, but if we consider the multiplication of matrix, it might be a difference. Yeah. Next, if A times B transpose is B transpose multiplication, matrix multiplication A transpose, and if you consider the size R times n, then it will be given n times m matrix, and in this case we define, since we define like this, B transpose is m times R, and A transpose, this size is R times n, and it will give m times n. So the size is can be satisfied this formula, and if you give each entries A, I, J, m times B, J, K, J from 1 to R, then you might give the R, B, K, J times A, K, I, and it not wait, J, I, then it is just change the i's rows and j's column to j's row and i's column of each matrices. I need more largely. A, I, J, B, J, K is the definition of A times B. Its size is n times R, R times n, and B transpose A transpose will be n times r size, r times n size, and its value, its matrix is written like that. V kj, because we define the transpose by changing the entries ij to ji. So if we define the entries like this, then its entries will be written kj and a is written ji. Of course, it is just changing I and k's position. So it is same. Okay. Yeah. It is just transposed I to k because its entry is written ik. Oh, not ki. And then the final property is commutativity of commutativity with inverse operation, and it is we can prove this simply by multiplying A transpose. It is identity matrix because by the definition of inverse, and we multiply A transpose for each side, both sides, then it is written AA inverse transpose by E, that by the property of E, and then it means transpose identity, but identity has only diagonal diagonal entries, so it is same to I. So it is true, then it is also true. Because it is the same equation. Next, I will enter the section 5 in chapter 1. Elementary matrix and method for finding inverse of A. In this section, we will construct some tools to find inverse of A, and I mentioned from until now it is important to find A inverse, because if we consider why we construct A inverse is we wanted to the solution of linear system. And if we have a proper inverse matrix, then it might give the solution X much easier. So it is very important information of matrix. So we will develop the how to find the matrix, inverse matrix. So the tool is elementary matrices. So until I will set first what we learned until now. In the matrix, we construct some operation of matrix, and it was it is called row operations, and there are some elementary row operations. Firstly, by multiplying a row by a non-zero constant, see, its mean is if we have matrix, and by multiplying C the R rows, we can multiply it as elementary row operation, and there is another elementary row operation by interchanging two rows, and it was, if there are two different rows, then we by changing R2, R1. It is also a kind of elementary row operation. And we learned addition of constant C times one row to another. That is, if we have R1 and R2, and then we will multiply R2 to C times R1, and it is also has same solution. So in these three operations does not change the solution set. So those are called elementary row operation, and we will construct elementary matrix from the three elementary row operations. Okay. It might be a different operation because we are considering the matrix as linear system. Then linear system has the unknowns a11 x1 a12 x2 equal b1. I will write just two linear equations. Then these row operations means just calculating these two equations. Like the first equation means the first operation means it makes C times a11 x1 plus C times a12 x2 and C times b1. And the second operation means just changing Wait, yeah, yeah, yeah. Not column. Yeah. So I will explain continuously. Yeah. So it yeah 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 right. Uh, I yeah. So I wanted to explain the third operation because it is just row operation. It's row operation and column operation means uh, another linear system. So if we see this equation, the third one means as column operation x2 plus no, a wait x2 plus a c times a11 x1 is right. I think I written differently. I rewrite matrix a11 a12 a21 a22 and the column operation will give a21 plus a11 yeah but as a matrix. No, just column operation as a column operation. Oh, 1 2 sorry 1 1 2 1 1 a22 a21 by multiplying c. And if we give this matrix to linear system, then it will give x1 prime plus x1 a12 plus a11 x2 prime a21 x1 prime a22 plus a21 times c x2 prime, and I will write another is same. Then its solution x1 and x2 is different from this system solution x1 prime and x2 prime because the equation is changed, but it has similar its solution is related to each other because if we define x2 prime is equal to x2 minus c times a11 1 over c times a11 x1 and x1 is x1. Then I think I'm wrong. I want to make original equation by changing the coordinate x1 prime x2 prime. Wait, I'm thinking time. Is zero. I have never tried to change the coordinate. A12 plus A11 C x2 plus x1 and then it will be A11. I missed. Maybe I forgot. Yeah. Yeah. Okay. Uh, uh, for using uh, that means we construct from row operations, but is there column operation? Yeah. So yeah, there are column operations also, and it also gives some good tools to find some other matrix form. Like if we want to get diagonal matrix, then if we use only row operations, then it might be hard. And also after then you might study about similar of matrix, and that means if we change the basis of matrix, then it by changing the basis we might have same matrix, and so from this process we want to get more efficient, having efficient calculation. So to construct the change of basis, we need column operation also. But it is very advanced concept, because until now we do not want to change the x1 and x2, so we are considering the only row operations, because if you want to understand the change of basis, it is also needed the concept of dual system I explained when I illustrate the transpose. So it gives so the row operation is used the multiply the column vector, but the column vector is used to multiply row vector to left side. And in this sense, we will multiply the row column and column vector. So in this sense, we might need to the operation of column operations. And it means similar to dual. And next, to get the origin, then we will construct elementary matrix, and it will represent those operations as the products of matrix, especially elementary matrix. So we will name to this matrix and the relation of matrices. First, the matrices A and B are, say, the row equivalent if either can be obtained from the other by a sequence of elementary row operations. It means operation. By changing the matrix by using row operation, if we made the from A to B some row operations A, then it is equal to B. Then it A, B are, we call this A and B are row equivalent, and also we will change the row operation as multiplication of matrix, and the matrix is called elementary matrix. I will write. Obtained from identity by performing a single row operation. I think if I give an example, then you might get these contents. Let me give one example. The first row operation was just multiplying the linear equations, one linear equation. Then if we made 3 by 3 matrix times 3 by 3 matrix, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, then its solution will be A11, A12, A13, 3, A2, 3, 2, A22, 3, A23, A31, A32, A33. Because by calculating the row column by using row column rules, and this is same to the row operation. So it is the first example of elementary row operation. And next, we might consider multiplying this matrix. Then by multiplying this row and column, then the if we choose second row, then it will be give third rows by multiplying each columns of this matrix A, and the third rows by calculating each columns, it will give second rows. It means the change of columns. So it is also a kind of elementary matrix, and so it is the second row operation. It means second operation. And thirdly, we might get third one by multiplying the matrix this. Then by multiplying the first row, we will get 2, 8, 2, 1. Oh, not 2, 3, 1. A 1, 2 plus 2, A 3, 2, A 1, 3, 2, A 3, 3. And another one is same because it does not change it from identity matrix. 2, 2, A 2, 3, A 3, 1, A 3, 2, A 3, 3. So it means the multiplication to the first row, the 2 times the third row. By multiplying 2. So these 3 operations are elementary matrix, and actually by performing one operation, this is from the matrix identity by multiplying 3 to second row, and it was from identity matrix by changing second and third row, and it came to the identity matrix by multiplying 2 and by editing the first row. So it is a single elementary row operation. We use only one row operations from an identity, so it is called the elementary matrix, and that means just representing from the row operation to matrix multiplication. And these three elementary matrix can be invertible. We have 3 elementary matrix, and it's simply row. Second one is interchange each row and editing the other one. C times another row. So the first one, the first elementary will be written like I will write more larger matrix. C. Oh, 1. Then it is just multiplying C to 1 rows, in this case third rows, and by multiplying one over C, because when we multiply C, it was non-zero constant, so we can define 1 over C, and another one is same. And by multiplying this, we might get identity again. And similarly, in the second row operation, we doing the second operation one more, then it will be changed to original matrix. So I will write simply. The row operation will give R2, R1, but if we perform one more, then it will be the original matrix. And third one is, since we adding the another rows, so by subtracting the rows, the row operation, we can get original matrix identity. CR2, oh, not CR2. It gave us R1 plus CR2, R2, and by subtracting that operation, we will get minus CR2. It is same to R1. So we get the original matrix. So these three elementary operations, the three elementary row operation can be written the multiplication of elementary matrix, and these elementary matrix are all invertible. So by using this, I will write on a theorem. We consider A is n times n matrix, square matrix. The following are all equivalent. It is equivalent theorem. This means the following are, yeah. The first one is A is invertible because we want the information of invertible, and and to get this information, we will construct another statement as trivial solution. It means if we construct homogeneous polynomial, then it has only one solution. And the third one is the reduced echelon form. We use the echelon form of A is identity. And the final one is A is expressed over as the product of elementary matrix. Actually, if I prove from A statement to another one, then it will, by using same contents, we can get another proof. I will prove all things. First one. We prove A to B. We will prove by proving this way. So if A is invertible, by the A statement gives A is invertible. Then we have inverse matrix. I will write this. Is satisfied A inverse A's identity. So we want to get this homogeneous linear system solution. So is 0 by multiplying A inverse each side to each side. A inverse A0, we get identity x equal 0, so it gives the solution is only 0. And next, we will prove B to C and C to D. So first, I will assume the statement of B. Assume AX equal 0. Then x equal 0. The C statement said reduced echelon form is identity. Wait. Okay. Wait. I forgot. It has trivial solution, and so I remember. If consider A is augmented coefficient matrix, and by multiplying xn with that, then each matrix is each entries are all 0, so this implies identity matrix, identity matrix times x is also 0, then there are some elementary row operations we can construct from A to identity matrix, because these are same linear system, and the elementary row operation, by exchanging the elementary row operation to elementary matrix, we might get the statement D, and it will be written multiplied each elementary matrix to A is identity. So and finally, I mentioned about that each elementary operation is invertible, so it will give A is ER inverse, ER minus inverse, E1 inverse. And this means by each vector matrix are all invertible, so we get A inverse by calculating this matrix's inverse, because inverse of inverse is same. By defining A inverse matrix like this, then we will get this equation. So since we find the inverse matrix of A, so if it can be written by elementary matrix, then it is invertible, because elementary matrix is invertible. All invertible matrices. This theorem also can be interpreted as the sequence of row operation I will explain until this, and we will take rest time. Constructing the reduced, we made reduced echelon form. Use the echelon form, and by making this form from we made A to I, and if we do this sequence of operation from I identity matrix, then it will give A inverse, because we A inverse defined the elementary row operations from identity by multiplying E1 to ER. So this sequence will be give from identity to A inverse. And finally, by using this, we might get the A inverse by using hand, by hand operate calculation. Okay. We might get A inverse. So it is a tool of how to get A inverse matrix by using elementary row matrix, elementary matrix. Okay, let's take rest time. Okay, we will continue slowly. I will enter the section 6 is more on linear system. And inverse matrices. We see some. We have seen some properties of inverse and inverse matrix, and in this section we will give more properties, more theorems for invertibility. And so first one, in the section 1.1, we learned there in the linear system there are three cases of the solution set. One is there is no solution, and there is only one solution. Finally, there are infinitely many solutions. But I explained it by drawing some plan or lines, but it is not rigorous proof. So since we learned the operation of matrix, I will prove about that. Linear equations. Has 0, 1, or infinitely many solutions. Firstly, if we get the two kinds of solution set case is familiar, and we know some. We have seen some examples, and another one is 2 makes 3 case. We will consider more than one solution. If it has more than one solution, then it should have infinitely many solutions. I will prove that. So let's assume that there are 2 different solutions, x1 and x2. Different solution. then we then we might make another vector by subtracting two vectors. x1 and x2 is different, so x0 is non-zero, is not zero. And also it satisfying that a x0 is equal to a x1 minus x2. By distribution rules, it is written a x1, a x0, or x2, and it was a solution. No, it was a solution of linear system. So it will give we made the linear system to a x equal b. Then if we substitute x to x1, then it will give b, and x2 is also will give b. Then the solution is 0. From this, if we construct another solution by multiplying x1 plus k x0, k is just any arbitrary scalar, then it is also will give this equation. And we know the solution. X1 was solution, so it will give vector b, and a x0 we calculate it is 0, so it is 0 multiplied by k, and 0 vector multiply k is 0, so it gives b. Then it means x1 plus k x0 is also solution of the linear system. And by choosing another scalar k, we can get infinitely many solutions. So it means if we have two different solutions, then it will give infinitely many solutions. And then next I will introduce some uniqueness of invertible matrix. Some uniqueness. First, the solutions uniqueness. If A is an invertible n times n matrix, let's think about this stuff. For every n times 1 vector b, the system of equations A has exactly one solution. and it is given by A inverse B. So it is our aim in origin. So I will prove it. We have the linear system, and in as the vector, if we multiply identity, it does not change it by the definition of identity, and it can be written A inverse by the definition of invertible matrix. So if we consider it from this, then it is same. So it means X is A inverse multiply B vector. Actually, by multiplying A inverse for each side, we get that. So by using this property, we might get the solution of the following linear system. When we first solve this system, we just use row operation, and it takes a lot of time. We use the Gauss-Jordan elimination, and it sometimes takes a lot of time to calculate by hand. But if we change it, the matrix multiplication of 1, 2, 1, 2, 5, 0, 3, 3, 8, x1, x2, x3 equal 5, 3, 17. No. And if we define this A, then by using this theorem, and I explained how to get the inverse elements by using this property. By making identity, we get inverse of A. So from this, if we get the solution in A inverse, then we might get the solution X A inverse B is 5, 3, 17. So if we calculate it, then we will get the solution. I will note it, and if you want, then you can try this. I skipped the calculation just so if we get the inverse matrix of A. No, it is square matrix because A was square matrix. Oh, I believe. It is the solution. I skipped to get the solution, and it is 3 by 1, and it is 3 by 1. So by calculating, takes a lot of time. Yeah. Right. Uh, in example, then I will solve this example in now. I think after then we do not try in this class because it is very good tool to get inverse matrix, but we can calculate only 4 by 4 or 5 by 5 by using hand. Although it is good tools, it takes a lot of time to get to find a inverse matrix. So more sizes matrix. Maybe I will explain determinant further concept, but in this section we will use just metric. We do not use determinants, and I will let me start with the example 50338 x1 x2 x3 equal 5 3 17. Then we denote this AXB, and then by adding identity matrix to right side, by making identity to left side, we can get the inverse matrix of A. So I will multiply 2 and subtract to second row. First row, second row, third row. So R2 minus 2R1 and R3 minus R1. 0, 1, minus 3, 0, minus 2, 5. If I wrong, then please notice it to me. And I will calculate second and third row by adding 2 R2 to R3, 0, 0. Forgot something. 0 is in. Right side. Okay. I forgot the right side. I just made identity. 1 0 0 1 minus 2 1 0 minus 1 0 0. Okay, thank you. To R3 plus 2 R1 R2, then 0 1 minus 3 0 0 minus 1, and the right side is minus 5 2 0, not 0 1. and I will multiply -1 by multiplying by calculating R2 plus 3R3 and R1 minus 3R3. Then the left side is 1 2 0 0 1 0 0 0 1, and the right side is -3 times 5 plus 1 is -14, and another one 6 and 3, and multiply 3 and adding to second row, -5 -3, 5 -2 -1, and finally by calculating R1 to R1 minus 2R2. I think my calculation is wrong. it is different. The first one I calculated. Wait. I'm with this arithmetic calculation. R2 minus 2 R1 minus 3 minus 2 and 3 to 3 minus 1 minus 2 minus 1 minus 2 5 minus 1 1. Is it right? 2 minus 4 2 I think it is right. I will calculate continuously. Left side is identity matrix and the right side is -2 -4e -2 16, but it is right. I'm not wrong. 6 9, and another one is same. Then it is identity matrix and A inverse matrix, so we get the inverse matrix of A, and by multiplying B to the matrix we can get the solution. So the solution X is -40 16 9 13 -5 -3 5 -2 -1 multiply to 5 3 17. It is A inverse multiply B, and by calculating this we might get wrong. In this way we can get the solution, and actually by using computer we might get the faster. Next one, 2. Is it right? Yeah, the second one. Oh, 51. Then 1660. Oh yeah, okay. So from this process, you can get the solution. Although we do not use row operation directly. Okay. And then by constructing this equation, we get the solution. And I want to generalize this form. And if consider the sequence of linear system, having same coefficient matrix, B1, B2, but there are some solution vectors, B1 to Bn, then you might construct A x equal B1 like this, and by using this form, we might be able to, for invertible A, x is written x1, x2, and this form, and its coefficient is same, so by constructing the matrix A, B1, B2, Bn matrix, then by making identity matrix, we might get or solution of this sequence. Identity x1, x2, xn. If your equation is identity, the right side, then it will be the inverse matrix of A. In my notes, there are some exercise also. So if you want to more example and exercise, then please check my notes. When we define the invertible matrix, we should satisfy this two-side equality, but in this theorem said we need just one, if we give just one side, then it will give invertible matrix B or A. So let A be a square matrix. If we just change the left side and right side, so I will prove only one side. Then B is equal to A inverse. It means B is invertible and the invertible matrix is same to the inverse matrix is same to A. Also, we might consider the change case also give the same result. If A was invertible matrix, then it will be easy to show because by multiplying A inverse, I will prove A case. B A equal identity. If A is invertible, then there is A inverse, and by calculating A inverse to both sides, then it will give the result if A is invertible. And we also should consider an invertible A. When we do not know whether A is invertible or not, then we might construct a homogeneous polynomial. If we construct the homogeneous polynomial, then by calculating B for each side, we will get this form. And in the condition, in our assumption, there is BA's identity matrix, so it will give the solution is a trivial solution. And as the equivalent statements, we have invertible A is invertible is same to this equation has only trivial solution. So this means A is invertible. And so we get the invertibility of B and A. And from this, if we calculate this, then we get B matrix is A inverse. And similarly, we might get when the matrix AB is identity by constructing Bx0 equal 0, we might get same solution, same result. So those theorem I explained. One is the uniqueness of solution, and this theorem, immutability. We can develop the equivalent relation of invertible matrix. In AX equal B is consistent. That means it has solution for every B. And actually it is almost the same to the F statement. F statement is it has exactly one solution. Actually, we can consider the B statements by changing the solution vector B from homogeneous polynomial. It does not change the number of solutions. So its proof is similar to this theorem's proof, because if we assume that A is invertible, then we might have A inverse matrix. Then by multiplying the inverse matrix, we get F, and F means it means has a solution. That means it is consistent. Consistent means having more than one solution. And it also, by constructing identity, by constructing the sequence of linear system, this, and we will get 1 0 0 0 0 1 0 and 0 0 0 1 by constructing the vectors. For every vector we have solution, and if we construct like this, then it will give the augmented matrix A identity, and by making these two identity, we can get the inverse of A from this. So if it has all solutions, then we might get the invertibility of A. And the final theorem of this section is that after we learned what is determinant, actually I explained in 2x2 matrix, only 2x2 matrix, then it is very trivial concept, because but we didn't learn what is determinant, so but it is very important information in invertibility. Both are square matrix. So I will introduce this theorem. AB is invertible. Then A and B are all invertible. So this means if at least one there is one non-invertible matrix, then by multiplication the matrix, the result matrix is also non-invertible matrix. And it also means all invertible matrix is from identity by operating some elementary row operations. Also, first, to show, I will show B is invertible. Then, by showing B is invertible, we will construct B inverse. Then it will make invertibility of A. So construct let's construct a homogeneous linear system. Bx equals 0. Then, for the solution of this linear system, we might get the next one, the following, by multiplying matrix A 0, and we know that AB is invertible, so A B inverse A. I mistake to explain. Wait. This is vector, and I will calculate following this. A Bx, because matrix multiplication is satisfied associative rule, and Bx0 is a solution. X0 is a solution of this linear system. Oh, wait. Okay. I mistake. In this equation, we will get the by using this AB since AB is invertible, so its solution is exact and it is trivial solution. So it will give trivial solution x0 is 0 vector. And this means we started to set by the solution of bx equals 0, and then the solution was trivial, it has only trivial solution. This means B is invertible by the equivalent statement. Invertible. So by constructing the next, by constructing A equal B times B inverse, it can be written AB and B inverse. So as multiplication of two invertible matrix, we can get A matrix is also invertible. So if A times B is invertible, then A and B are all invertible matrix. Finally, I will explain some forms of matrix. It is the final topic of today. There are some forms of matrix. One is diagonal and two kinds of triangular matrix and the symmetric matrix. In the definition of matrix, we just define it rectangular arrays, and so there are some kinds of form of matrices, and we will divide it by like this. We will name the special form of matrix as diagonal, triangular, and symmetric. First one is diagonal matrix. As the name, it is a diagonalistic matrix, so we will consider square matrix A, and its matrix is or the entries are 0 except the main diagonal entries. That is, if we denote the entries of ij position, like aij, then it is 0 when I and j is different. It is so. Let me give an example of diagonal matrix. Of course, 1 by 1 matrix has only one entries, and its entries position is one row and one column. So any 1 by 1 matrix is also diagonal. And of course, if we consider like these matrix, identity is also has only the main diagonal entries, so it is also diagonal matrix, and geometrics also diagonal matrix. And maybe I will skip the proof of this theorem. I write down in my notes the proof, but it is short, and if there are some rows, its entry is 0, then it will give infinitely many solutions, so the diagonal matrix will be non-invertible. So this theorem is say that a diagonal matrix is invertible if and only if all of its diagonal entries are non-zero. Its property is happen from triangular matrix also. So I will explain what is triangular matrix, and it is more general. It is generalized from diagonal matrix because it is very useful to calculate in matrix multiplication, because if we calculate two diagonal matrix, then by the row column rule we will get the diagonal matrix. And so it is very useful to calculate in matrix system, but its condition might be strong because there is no any entries in other position. So we will define more generalized matrix, which is called the triangular matrix. And there are two kinds of triangular matrix. One is upper triangular, another is lower triangular. We consider the square matrix, so in the upper and lower matrix case also we will consider square matrix. The matrix is called upper triangular, if its entry all entries below the main diagonal are all 0. So if we see the diagonal matrix, then it has only the main diagonal parts, and then it will divide 3 parts of matrix, the main diagonal and the below of the main diagonal and the upper side of the main diagonal. It means if we denote the ij's row and column, denote like this, then if the rows number is bigger than columns number, then it will be 0. Similarly, we might be able to define lower triangular its all entries above the main diagonal or all 0, and of course it means aij is 0 when j is bigger than I. So if I give an example of this matrix, if there is only upper triangle side, then it is upper triangular matrix, and conversely, if there is below side and the main diagonal entries, it has the entries of below side of main diagonal and has entries on the main diagonal, then it is called it lower triangular matrix. So by the definition, we made this definition from diagonal matrix, and actually diagonal matrix has only diagonal parts. So if the matrix is upper triangular and lower triangular, then its matrix is diagonal matrix. Okay, the time is remaining 5 minutes, and so I will skip a theorem, and this theorem means the upper triangular matrix's transpose is lower triangular matrix, and if we see the condition this, then we can check easily. And there are some other properties. I explained diagonal matrix multiplication, but if we multiply two diagonal matrix, then it will be also diagonal matrix. Every triangular matrix is also closed under the matrix multiplication. So if we calculate two upper triangular matrix, then it will be upper triangular. Of course, it is satisfied in lower triangular too. And so in this sense, the inverse of an invertible lower triangular matrix is also will be lower triangular. And if you learned about the adjoint matrix, then its proof will be easy. So it will be proved easily. So after I explain what is adjoint matrix after class, I will prove this statement. And finally, I will explain the symmetric matrix. Simply for let A be a square matrix if A is same to A's transpose, then it will be say to be symmetric. And if we see an example, then it looks like this form. So it has same value of entries for each transpose side. So diagonal matrix is always symmetric matrix, like this. So there are some properties of symmetric matrix. If A, B has same size, then same size and symmetric matrix, then A transpose is also symmetric, because by the definition we can see this easily, because transpose is original matrix. And A plus B and A minus B are also symmetric. This means symmetric D is closed in additional operation. However, if we multiply two symmetric matrix, then it can be unsymmetric also. It could not be symmetric. Yeah, sometimes it can be, but not always it is symmetric. However, if we calculate just the scalar, then it is symmetric. Okay. And also